Okay, right. So yeah, the recording has started, and now we will cover the new stuff, right? That which is the probabilistic graphical models. So let me just share the screen again. Okay, this is available. Let's go back here and so close this thing. Write a new notebook. Create. Okay, we are here. Right. So, right. So let's so this will be so that was just preliminaries. Okay. Let's look at the new stuff now, which is probabilistic graphical models, right? So okay, so let me write that thing down. So this will be about probabilistic graphical models, which is which is something which is very basic actually, probabilistic graphical models. Okay. Uh, okay. So okay, so first of all, I'll just recap, right? So what is the definition of KL divergence that we just saw? That was KL between P and Q. That is equal to nothing but expected value under P of X log E of X by Q of X, right? So again, I mean, if you want to, if this equation doesn't make sense, or rather it looks very complicated, right? Then you can think about it as a distance between P and Q. That's all. So yeah. So what is the I mean what are what is probabilistic graphical models and why do we want to study them, right? So this is PGMs. This is shorthand notation for that, right? So why do we want to study it? What is the objective and so on and so forth. So let us write that thing down very explicitly. So there are two objectives here. Okay, so there are two objectives. What are the two objectives? First objective is, so in generative modeling, in general, there are two objectives that we want to learn the underlying distribution. Right. So, for example, let's say we have, for example, let's say we want to generate images. We can think of images as a random variable, right? And so to basically generate new images, we need to know or we want to learn the underlying distribution of the images so that we can generate more images, right? That is how you can think about the generative modeling in general, right? You have a random variable. All you want to do is you want to learn the underlying distribution so that you can sample from that distribution and generate new representatives of that distribution. That's all. What is the second objective though? First is, of course, learn the underlying distribution. And the second objective, which is what is practical, is that we want to sample from the underlying distribution. So we want to learn the underlying distribution, but just learning the underlying distribution is not enough. Okay. We should be able to sample from the distribution as well. So, uh, I mean, uh, that is what is so these are like the two essential goals or two main goals of uh, generative modeling in general. Okay. So So how does so basically probabilistic graphical models will give us a sort of a very formal framework to work with these things. Okay, work with generative models, latent variable models, and so on and so forth, which will help us essentially in our objective. Okay, so let's get started with PGMs. Okay, so what is a probabilistic graphical model? What is a PGM? Okay, so very in very simple uh, very simple there's very simple way to what say what a PGM is. Okay, it is nothing but a set of random variables associated associated with a graph structure. So what do I mean? So you have a random variables. Let's say you have, for example, two random variables. Let's say x1, x2, and x3. Okay. And these random variables are now associated with each other through via a graph structure. So maybe the graph structure could look something like this is x1, this is your x2, and this is your x. Maybe make this x3 and make this x3 and make this x2, something like this. So a graph has nodes and vertices, right? Or sorry, a graph has nodes and edges. So maybe so each node basically represents a random variable, right? So x1, x2, x3 are your three random variables. So your graph has three nodes, okay? And then there are some edges on top of it. So maybe the edges could look something like this. So you have x1 to x3, you have a edge. You have a edge from x1 to x2, and then you also have a edge from x2 to x3, right? So this is basically what a probabilistic graphical model is. Okay. Now, so you might question, right, that why is this thing required? I mean, why do we need so okay, random variables is something that we can understand that okay, for generative modeling, we have some for example, we have images. We can only look at the sampled values. So we can only look at the images. We don't know the underlying distribution. So it makes sense to talk about random variables. But why are we talking about graphs on top of it? And then, and like, why do we want to associate random variables with these graphs? So, so this might be a question that might come to our mind, right? So, so to motivate the idea of probabilistic graphical models, what I will start with something which is very simple. Which let's start with simple Bayes rule. Okay. So let's say so you have three random variables, right? So you have so if you have three random variables, you can write down the joint distribution of the three random variables, right? So that will look like P of x1, x2, x3, right? Using Bayes rule, what can you how can you write or decompose this distribution? You can write this as P of x3 given x1 comma x2, P of x2 given x1, and P of x1, right? So this is simple Bayes rule. This is nothing but this is simple Bayes rule, right? So nothing fancy, just simple plain Bayes rule. Now, uh, similarly, you can also so Bayes rule is applicable on any kind of distribution, right? So even if you have, let's say, four random variables, you have x1, x2, x3, x4, right? You can write the joint distribution as P of x4 given x1 to 3, right? P of x3 given x1 1 to 2, P of x2 given x1, and P of x1. So uh, now mm, what you can actually do is you can represent this So, I mean, this is a decomposition of the joint distribution, right? You can actually use probabilistic graphical models to actually represent this particular structure or particular decomposition. How? So what you can do is you can see that okay, x1 is something which is very as which is required for each of the conditional distributions here, here, and here, right? So maybe make one node as x1. Okay, then once you have x1, you can then calculate p of x2 given x1, right? So then you have x2 and you have a edge connecting x1 to x2, right? Then once you have both x1 and x2, you can sample x3, right? So maybe you can then have x3 as another node, and this has two nodes incoming, one from x1 and one from x2, right? And then you have, once you have all x1, x2, x3, you can now sample x4. So that will become another node in your graph, and that will have edges from all the other nodes, right? So something like this. Now, so this is a this is again, this thing is now a probabilistic graphical model. So this is a PGM. So you can always have a distribution like this, right? A decomposition like this, and you can construct a corresponding PGM like this. Okay.
So
Uh,
what if I do not have an edge in between, say from x2 to x3?
so if you don't have a edge from x2 to x3, the decomposition will change, right? So so right now we are looking at the decomposition and then we are constructing the graph. So, so in that case, let's say if the decomposition was something like, uh, let's say if the decomposition looked something like P of x for given x1 to 3, okay, P of x3 given x1, P of x2 given x1, and P of x1, right? If you had this kind of decomposition, then what you said would look something like x, you have x1, right? You have x2, you have a graph from x1 to x2. Then you also have x3 where the only incoming edge is from x1. And then you have x4 which has incoming edge from all the above nodes, something like this. So this decomposition will correspond to this graph,
Yes.
right? So, going from a decomposition to a graph is something which we can easily do. But what we would actually like to do is the other way around. We would, so I mean, practically speaking, what we will do is we will first construct the graph and then we will go to the corresponding decomposition. That is what is of our interest. I mean, because graphs allows us to basically think about, so basically PGMs will allow us to think about the random variables in an intuitive manner. For example, let's say there are three, four factors, right? Uh, it it is very difficult to think that, okay, what should be the distribution of this factor given the other factors and so on and so forth. But it is very easy to think about these factors in terms of graphs, right? For example, we know that, okay, factor one will influence, let's say, factor two and factor three. However, it might not affect factor four. And factor two is only influenced, it just influences, let's say, factor four, something like that. So we can just think about uh, uh, what node is influencing what other node, and we can construct a graph. And once we have a graph, we can then go to the corresponding decomposition. Okay. But so that is what we would like to do. So that is why PGMs are so important or so helpful. It allows us to sort of, think about the real world phenomena in a very intuitive manner, right? Right. So that is why we are going to sort of work with PGMs, and that is basically our uh, framework that we are going to work on. But one question is that, is this graph unique? Is this graph we got this graph, right? We had a joint distribution. We came up with we decomposed it using the Bayes rule, and from there we came up with this graph structure. But the question is, so I mean, what do I mean by is this graph unique? What I want to ask is this the only graph structure that will determine my joint distribution? That is the question. Well, I mean, if you think about it, that's not true, right? For example, you can have P of x1, x2, x3, and x4. You can, instead of decomposing it like this, what you can do is you can decompose it like this: P of x1 given x2 to 4, that P of x2 given x3 to 4, P of x3 given x4, and P of x4. Now this graph will have x4 as the parent, like the most ancestor node, and then you will have something which will come to x2. Sorry, first you will have x3, right? So x4 is influencing first. X3 is only influenced by x4, so you will have this one. Then you will have x2, which will have nodes incoming from both of these two nodes, and then you will have x1, which will have nodes incoming from all of the other nodes, something like this. So this graph also determines the joint distribution, and this graph also determines the joint distribution. So both of the graphs determine the same joint distribution, right? So I mean, uh, a joint distribution can have multiple uh, representations in the graphical form. However, let's say if I tell you that okay, the graph. So let's try to think about the other way around, right? Let's try to think about graphs first, and then we will try to come up with the joint distribution. Let's say okay. So I mean, this will sort of help us to appreciate why we are working with PGMs. For example, if I give you this structure, or if I give you this structure, both of the structures will give you the same joint distribution, right? I mean, going from joint distribution to the graphical structure uh, uh, is not interesting. I mean, you can always come up with multiple combinations of the node. I mean, this is just another way to decompose it using Bayes rule. You can also decompose it in another way, right? You can use P of x3 given x1, x2, x4, so on and so forth. I mean, going from joint distribution to corresponding graphical structure is not interesting. What is interesting is that you have been given a graphical structure, okay, and from graphical structure you come up with the joint distribution. That is what is interesting. So let's try to get a feel of it, right? Let's say you have x1, you have x2, you have x3, and you have x4, right? And the graphical structure looks something like this, something like this. This is the PGM, for example, let's say. And you want to basically comment on P of x1, x2, x3, x4, the joint distribution of the four random variables, right? Now, from using this graphical structure, what can we write? So, I mean, the simplest way to start with this is you start with the most parent node, right? Which is x1, because there is no incoming node to x1. You start with P of x1. So you have P of x1, right? Then x1 influences x3 and x2. So both of them will have P of x3 given x1, and x2 will also be P of x2 given x1, right? And then you have x4, which is only influenced by x2. So you have P of x4 given x2. So this is the joint distribution of all the four random variables. And to appreciate it, think about it, right? If you use Bayes rule to write the same decomposition, what will it look like? That would look something like P of x1, P of x2 given x1, P of x3 given x2 comma x1, P of x4 given x1, x2, x3, right? Now this is from PGM, right? This we obtained from PGM, and this is from Bayes, right? This is from Bayes rule. Now think about it, right? So P of x1, P of x1, okay, both of them are same, no problem. P of x2 given x1 is here also, P of x2 given x1 is here also. Okay, there is no, it's good. Both of them are same. But now look at this distribution. This distribution is basically telling you that x3, to calculate x3, you need to calculate x1 and x1, x2 and x1, both of them. However, if you have the knowledge of this probabilistic graph or the graph structure, you can directly say that, okay, once you have the information about x1, you can directly get the x3. Okay. Similarly, here the Bayes rule is telling you that to calculate x4, you need to know about x1, x2, and x3. However, the PGM is telling you that, oh, you just need to know x2, then you can get sample x4. So this is what PGMs do. They add additional structure on top of your random variables, and because of that, the decomposition becomes much simpler compared to Bayes rule. Is that clear? Does that make sense?
So, but then both the processes are equivalent. So, I feel that it doesn't matter that whether the graph is given and then we can write its
No,
corresponding joint distribution, or the joint distribution is given and then we can develop a graph out of it.
no, no. So, no, that's not true actually. So, from the Bayes rule, so if you think about it, what we are basically saying that P of x3 given x2 comma x1 is equal to P of x3 given x1, right? This is a big statement because it is saying that given x1, x3 is independent of x2. This information is not conveyed from Bayes rule, right? This is only conveyed through this graphical structure.
It's true that I was talking about the first process and the second one. So in the first process, from the given, we were given an equation, and then from the equation we derived its corresponding graph. And now in this second process, the graph or the interdependency among the random variables is given, and then from there we are, writing the joint distribution.
Oh, no, no.
It's
So basically, in this process, we have the knowledge of the graph beforehand, right? I mean, if I don't, if I sort of remove this graph, uh, if I don't give this information about the graph, you cannot write this thing, right?
Yes, and in the first case, wherein the equation was given, and then we came up with the graph
So this
corresponding to
was,
that.
so this is your, this is the complete, so this is the graph corresponding to Bayes rule, right? So this is not informative at all. I mean, so this is like basically this is a brute force way to write your joint distribution in some sense. Here it's more like you know the additional structure that is there on the random variables, and hence you can just work with this thing.
Okay, and
So
how do we
maybe I
know?
think sorry.
Yeah, yeah. Please continue. Yeah.
So maybe what I want to say is that we don't know this decomposition beforehand. We know this decomposition only if we know the graphical structure on top of it. If
Yes,
we knew
and
this
how?
thing, if we knew this thing, then we could of course write the graph down, and your what you're trying to say is would stand correct that both of these things are same. But what I'm trying to say is that if you know this structure, then you can write this thing. If you don't
Yes,
know this structure, you will only be able to write this the decomposition using Bayes rule. Yeah,
yes, yes. Right. And how do we determine the dependence among the different random variables through the
right.
data or by some other means?
Yes, yes. So that is we'll see that. So we will start with latent variable models, and I mean, in fact, there won't be a lot of nodes there. There will just two nodes, a latent variable and your observed variable, so Z and X. So that. So we will, so though I am working, I'm sort of explaining graphical models here with a lot of nodes, but the graphical model of our interest will just be a simple two node graphical model, and we will just work with that. So and there and we'll see that. I'll try to explain what it is exactly.
Okay, okay, yeah.
Right. So So I think this is the right time to bring something which is of our interest, right? So which is the generative view of PGMs. So what is this generative view of PGM? So let's take that same example that we had here, right? So let us look at the same example. So you have x1, you have x2, you have x3, and you have maybe for the sake of, to avoid any redundancy, I'll just add another node from x3 as well. Okay. So if your problem statement, if I, so the problem statement, or rather the objective is, let's say, to sample x4. This is what is asked of us, right? So we want to basically sample from x. So we want to sample x coming from p x4 give of x, right? So we want to sample from this distribution basically. Okay. Uh, how can we sample from this distribution? Uh, well, it's so one way to do this is you write the distribution of x4, right? P of x4. Let us for now let us assume that both all of x1, x2, x3, x4, all of these are discrete random variables. But you can easily extend the argument to continuous versions as well, right? So how can you write P of x4 in terms of joint distributions of x1, x2, x3, and x4? It is quite simple. You use the marginalization property, right? So you can write this thing as P of x1, x2, x3, x4, right? And sum it over x1, x2, and x3. Okay. So this is your marginalization of random variables, right? So you want the only quantity of interest is x4, and so you marginalize out all the others. That's simple probability, right? Now, what can you? So now you have the joint distribution here, right? Now this is what is interesting, because once we have this joint distribution, now we can actually exploit this graphical structure, right? What we talked about here, that once you have the graphical structure, you can exploit it to write uh, a nice decomposed form. So what you can write it, so you can basically write this thing as summation over x1, x2, and x3. And you can write P of x4. X4 only depends on what? X2 and x3, right? X2 and x3. P of x2, x2 given x1, P of x3 given x1, and P of x1, right? This is how you can write the distribution of x4 now. So how will you sample from it though? So it's quite simple. If you have the graph, you can sample from it. How can you sample from it? So uh, first sample x1 from P of x1. So here we'll assume that x1 is easy. So I mean, we can sample from x1. That is something that we are going to assume, that the oldest node, or the most ancestral node, we can always sample from that. Otherwise, we cannot sample anything, right? So we need to be able to sample from x1. Okay. Once you sample from x1, then you sample x2 from P of x2 given x1. Okay. Because that is what the graph is telling us, that once you have x1, you can sample from x2 as well using this conditional distribution. Similarly, now sample x3 from P of x3 given x1. Okay. Because again, the graph is telling us that if once you know x1, you can sample from x3. Okay. And finally, when you want to sample x4, you sample from P of x4 given x2 comma x3, right? Because you have sampled x2 and x3, you can use those to sample from x4, because that is what the graph is telling us, right? So this is like a generative view of PGN, right? So this thing is corresponding to basically your graph, right? So you have x2, you have x3, you have x4. So this is the generative view of your uh, PGM. So what do we mean by the generative view is the quantity of interest for us is just x4. Okay. However, we are not able to sample x4 directly. So what we are doing is that we are instead making use of this graph. Okay. And we are sort of seeing that, okay, to sample x4 first, we need to sample x2 and x3. And to sample x2 and x3, we need to first sample x1 and so on and so forth, right? So, so this is like a generative view of how you can interpret the PGMs. So basically, given a graphical structure, right? If you are given a PGM, the PGM is actually telling you that how you can sample different nodes using the previous nodes. That is what the PGM is telling. That is the generative view of PGM. And this kind of sampling is something called ancestral sampling, right? Ancestral sampling. So why the word ancestral? It's quite intuitive, right? Because to sample from any node, if you want to sample from this node, you need to sample its ancestors. And if you want to sample from this node, you need to sample its ancestors, so on and so forth, right? So this is like a so you can think of if you have been given a probabilistic graphical model, if you have been given a structure on random variables, you can look at it as a from a generative view that okay, this node is depends on this node. So if I want to sample from this node, I need to sample from this node, and so you can think about different techniques and like other stuff, right? This is
So what is the one question?
yeah
Hello.
yeah
What is
yeah
the
yeah.
difference between the notation of probability you have written in this slide and previous slide?
Which one? Which can you point out? Do
Yeah,
you
yeah.
mean this one?
This one and same thing you have written differently, right?
Where? Where?
P of x2 given x1 you have written okay okay different notation in the previous
Like
slide.
this? Like this?
Yeah, yeah. But
Oh,
here you have
both of
written
them
different.
are same. So I mean, okay. So basically, I mean, so this is
Here
a
you
little
use
abuse of notation. You can think of this as x2 given x1, right? So
okay.
this is just yeah, my bad. So it is a sort of a notational rule that if you are writing, let's say if you are writing p of x, you also, so x is just a placeholder, right? You so to explicitly tell what is the random variable, you should write the name of the random variable here. But I mean, yeah, we often abuse that notation and just write p of x to given x1. But yeah, I mean, you can write it like x2 comma x3 so on and so forth. That is fine. I mean, no issues. I mean, if you're, yeah, maybe I'll be explicit from next time. Yeah. Right? Yeah. Yeah.
So I have a query here. So do we allow cycles in the PGM?
No. Yeah. So that's another thing, right? So if you have cycles in a PGM, basically there is no ancestor. There is no concept of ancestor then, because you will basically end up with a contradiction, right? So you will start with one node. And if there exists a cycle that allows you to come back to the same node, so you will basically have that uh, a particular node is the ancestor of itself, which is basically moot, right? I mean, uh, that's why we don't allow cycles in the VGM. Yeah.
Okay.
And
So
I
this
mean,
And
if you
means
think
their
about it,
guides.
I mean, if you think about it from a distribution point of view, right? You want to write something like P of x3 given some random variables, right? If there is a cycle in this, this will end up being P of x3 given, for example, x1, x2, and x3, because there is a cycle from x3 to x3, right? So that will again you will run into a contradiction.
yes, And do we have, and how do we have rather the probability distribution of x2 given x1? Because individually we would be having the probability distributions for x1, x2, x3, and then x4. But from these individual distributions, so how do we usually construct, I mean, these conditional probability distributions?
We will see that. We will exactly see that actually.
Okay, okay.
Yes. So big. So
So that
I
means
mean, if I have to, okay, please go ahead.
these are DAGs, right?
Yeah, these are directed cyclic graphs. Yes, these are DAGs. Yeah, these are DAGs. Yeah, yeah, you are right. These are DAGs. Yes. Right. So this is this. Now let's think. Let's so this is basically all the understanding of PGMs that we need for uh, uh, our practice basically. Okay. So what but I mean, as I told, right, that essentially we are going to work with a very simple looking graph. So let me write that down. It is a very simple PGM that is going to help us. Okay. So the graph that we are going to look at is a very simple one. It is just you have one node, you have just another node, and there is just a single link between the two. Z from Z to X. That's all. Okay. I mean, this it might look like, you know, we talked about all this complicated stuff, but we are going to consider something which is so simple looking. This is simple looking because we are going to start with something which is very simple, which is VA. But we will see that when we go to standard mod, like more complicated models like diffusion models, this graph will become more and more complicated, right? So let's start with this thing. Okay. So let's say that so you have the underlying distribution, the underlying distribution for Z, which is Q of Z. Okay. And you want to sample X from end of the day, you want to sample from X. Okay, so you have X. How are you going to sample X? Basically, you are going to use the PGM. The PGM tells you that you sample from Z, then you can sample from X. So you are going to sample from P of X given Z, right? Just similar to what we wrote over here, right? Now, uh, so consider this, right? In generative modeling or in general in machine learning, you have this data set, okay? So you have a data set which has both Z and X. Okay, so you have X and Z. Okay, you have a data set for this. Okay, so there is a so there is an underlying distribution of the joint distribution X comma Z. Okay, you want to basically learn this distribution, right? You want to learn this joint distribution, which is P data X comma Z. To learn this joint distribution, what you are going to usually do is you're going to parameterize, you are going to use a parametric model P theta of X comma Z, right? And what you're going to do is you're going to learn this theta so that this P theta of X comma Z is close to P data of X comma Z. Does that make sense?
Yes.
Right. So there is this underlying joint distribution P data of X comma Z. What we want to learn this distribution, right? We want to learn this distribution. So we are going to use a parametric approach. So we are going to construct a new distribution P theta of X comma Z, again a joint distribution, but it is parameterized by theta. So you can think of theta as a neural network, for example. And you are going to learn this theta so that P theta of X comma Z is close to P data of X comma Z. Okay. This is our goal, right? But now how do we quantify this closeness, right? Right. We need to use some sort of notation of closeness, right? What is it that we are going to use? So if we recall in our preliminaries, right, at the start of what we saw is exactly something which is related to closeness of distribution, right? Which was the KL divergence, right? So we are going to use that. So we are going to obtain this theta star, which is argmin. So we are going to minimize over theta, right? So minimum. So this is the notation. Let me know if this is not clear. What is meant by argmin, right? Argmin of DKL between P data and P theta. This is what we are going to do. So we are going to calculate scale divergence between P data and P theta. Okay. And we are going to learn theta such that it minimizes the scale divergence. And whatever theta minimizes this scale divergence, we are going to call that theta star, and we are going to use that theta star for sampling. Okay. Is that clear? If you can just say yes or some reaction.
Yes, yes, it's clear. And what is the usual notation? I mean, we used to represent parameters. In some of the books or in the notes, I have seen it is theta, and in some of
Yeah.
the notes, I see, I mean, other symbols. So, what is the, I mean, common convention to
So
represent parameter?
so generally you use I mean there is no hardcore rule as to what is used, but you usually use theta, phi, these for to represent the parameters. Theta and phi, I think, are the most common ones. You generally
Okay,
use alpha, beta, and so on to represent the uh, scalar values or some sort of hyperparameters. So that is the general rule. But I mean, there is no hardcore rule. I mean, you can use anything to represent this
okay,
thing.
okay. And when we say that this, I mean, this theta is being learned. So, what
Yeah.
does it mean? That are we using some neural network or some other kind of the ML model or what?
Yeah. So theta, you can think about theta as a neural network. And basically, we will calculate this thing as some loss function, right? And we will optimize the parameters of the neural network to minimize that loss. That is what I
Okay,
mean by learning theta.
okay, okay. Thanks.
Yeah. Right. So this is how you will learn. This is how we will basically uh, do this thing, right? So what is this DKL between P data and P theta? So let us write that thing down. So DKL between P data and P theta. This thing is nothing but expected value under P data, right? I'm just writing that down the definition of scale divergence. So this is log P data over P theta, right? This is what it is. Now, what you can do is this is expected value of P data log of P data, right? Minus expected value under P data log of P theta, right? Now, if you think we want to optimize over theta, right? So your KL divergence consists of two terms. This is the first term and this is the second term. Now, please note that the first term doesn't depend, this thing doesn't depend on theta, doesn't depend on theta, right? So if this term doesn't depend on theta, you can simply like ignore this thing, right? This thing you can just ignore because this thing is not going to help us in our optimization. This is just like a constant that is added to our objective function, right? Because remember that we are going to do an optimization here. So any constant that is added to your loss function, you can simply ignore that. So you can ignore this first term. So this is basically your entropy term that you can simply ignore. That is not going to play any role in our uh, final optimization. Okay. So what does this leave you with? I mean, so so you want to do a minimization over theta over DKL between sorry DKL between P data and P theta, right? This thing is equivalent to since this since the first term is not dependent on theta at all, you can just work with the second term. So this is equivalent to minimization over theta of minus expected value under. So this is like the cross entropy term, right? So this is p data log of p theta, right? This there is a minus term here, remember. So minimization of a negative term is equivalent to maximization, right, of theta, and you just remove the minus term, right? So this is equivalent to maximization over this thing, expected value in the p data, log of p theta, right? Is that uh is that clear?
Yes.
And this thing is exactly what is referred to as maximum likelihood maximum likelihood estimation, or MLE for in short. So this is the MLE. So what this is what people call as MLE in general. So if you read like these any research papers or books, they talk about MLE estimate and so on and so forth. So this is what they mean by MLE estimate. Okay.
And how is this different from the cross entropy? I mean, if we just
Oh, so
replace this
so
p data
they're
by,
basic. Yeah, yeah. So actually, both of them are same. Actually, if you think this is nothing but your cross entropy, right? But it's just like the new term that people have given this thing. It's so cross entropy is something which nowadays is very much associated with classification problem. But if you look at it, even in generative modeling, you are using cross entropy, which results in this kind of this thing. So I mean, this is perhaps more intuitive to people that you are maximizing the log likelihood of p theta with respect to data. That is why they call it ML. There
two
is
terms are not clear
not
here. Yeah.
okay.
Yeah.
Tell
So,
me.
yeah. So the first term is the likelihood, and so how
Hmm.
this likelihood thing is different from the probability term which we have used so far. Number one, and
Hmm.
second, uh, it could have been cross entropy if instead of p data here, we have p theta. Then probably we can write the cross entropy here. And right now, this term is totally a new kind of the thing wherein we are computing the expected value of the log of the p theta is fine, but then over the
Hmm.
distribution of the p data.
Right. So, so Will, the the likelihood thing is basically, if you want to think about it, why are we calling it likelihood? Is because, uh, so okay, p theta is like a distribution on x or whatever x comma z, right? This is p theta is a distribution over x comma z. So you are basically, in some sense, what you're trying to do here is that. Uh, uh, I mean, how should I tell it? Mm, uh, you can think about it as follows, right? So you are trying to come up with a theta, p theta, which basically maximizes the likelihood of the distribution in some sense. I mean, how do you understand it is basically like you have p theta, which is a distribution over x comma. For now, just think about x. Okay, so you have you are learning a distribution p theta over x, and you want it to maximize log. So you are learning this theta so that log p theta is maximized, but it should maximize under the expectation of p data. Okay, so it's like so you are basically learning theta such that it should best uh, represent, or it should best model the data distribution, which is p data. I don't know if that makes sense.
Yes,
uh,
so like in the equation of the equation to compute the cross entropy, how do we write it? So do we write it like say minus the expected value of say
mhm,
log of the qx, and wherein we take the
mhm.
expected value over the px. Do we write it like this?
Yeah,
Uh,
yeah, so the cross entropy is your this thing, right, that you have expect. So cross entropy is something like this, right, log qx. something like this.
Yes, yes. Okay, so this indeed is a cross entropy only.
Yeah, 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 yeah. This
But
is
then,
this is a cross entropy term.
oh yes, and then you are, I mean, referring this term or using, I mean, this MLE interchangeably
Mhm.
for the cross entropy.
Yes. So yeah, negative of cross entropy is just MLE if you want to think about it that way.
Oh, I see. Because I very vaguely remember that the people, I mean, used to use the term expectation maximization kind of the thing to compute this MLE thing. So, but
No, no.
I mean,
So we will come to expectation maximization in a bit. So that is our
o-
next thing. So I
okay,
will
okay,
explicitly tell you why EM, where EM comes in. I will
okay.
exactly tell you why we need EM at all, and so on and so forth. So
Yeah,
just bear with me. So there is some problem with MLE that I'm not telling right now, and to alleviate that problem, we need EM.
okay, okay. So is this a
Okay.
right term, a maximum likelihood estimation or maximum log likelihood estimation? Would it be the right term or this
Both
MLE
are,
is okay?
you can think of, you can use any word actually. I mean log, like
Oh,
people use MLE, so maximum likelihood estimation is the common term. Yeah.
okay. Yeah, thanks. I
Yeah.
understood. Yeah, thanks.
Right. So practically what you are going to do is something like this, right? So you have a data set, right? So let's say you have a data set of xi comma zi, right? So this is I equal to 1 to n, which is your data set D, okay? And how are these samples coming? These are like sampled IID from your P data. So, I mean, think about images, for example, right? You only have, you know that there is some underlying P data. You don't know what this P data is, by the way, okay? But you have samples from that distribution, okay? And you want to learn a P theta, which models this P data. So, so what you are going to do is you are going to use this MLE kind of thing, right? So this is your P expected value of P data of log P theta of x comma z, right? This is what our MLE was, right? So this was our MLE objective, right? Now, what you can do, of course, is so whenever you have an expectation under a distribution in ML, in machine learning in general, the first thing that should come to our mind is that do we have samples from this distribution or not? In this case, we do have samples from this distribution from our data set itself, right? Why do we want samples from this distribution? Because we cannot calculate this expectation. I mean, this expectation is like, integral of P data and so on and so forth, right? That will be something complicated. We cannot calculate that. What we can do, however, is we can use something called uh, uh, law of large numbers, right? So what does law of large number, what it tells you is that expected such an expectation you can calculate by taking a simple average. That's all. So you can just do so you can replace this expectation by an average, okay? However, when you are taking the average, so okay, let me just go step by step. So you just take average, log average of this quantity, okay? Log P theta of xi comma zi. Okay, I goes from 1 to n. And where are these xi's and zi's coming from? These are coming from your data set D. So, is this clear? I mean, is that making sense? What I have done here is that you had expectation of this thing. You cannot calculate the expectation. I mean, in deep learning, in machine learning, it will be very rare that you will be able to calculate any expectation explicitly. You will always estimate that expectation, or you will always approximate that expectation using law of large numbers. So all you need to do is look at two things. Can I calculate the term which is inside the expectation? Yes, I can calculate, right? Because P theta is a parametric model which I am going to model. So I will know how to calculate this thing. And the second thing is, do I have samples from this distribution P data? Because the expectation is under P data, right? I can only approximate this quantity if I have samples from P data, and then I can take average. Is that clear?
Yes, yes.
Right? So now what does this become? So this is nothing but 1 by n. So this is summation of log. Summation of log is nothing but log of product, right? So this is log of product of I going from 1 to n, p theta of xi comma zi, right? And to what so this is now xi's and zi's are IID, right? So they are independent and identically distributed, right? So what you can do is you can write this as 1 by n log of p theta of x I comma zi, right? Uh, I going from 1 to n. You can write it like this: joint distribution of all the pairs of xi's and zi's, because they are independent. I mean, if you remember, p of x1 comma x2 is equal to p of x1 into p of x2, right? Because if x1 and x2 are independent, right? So that is what I'm using. So since xi's and zi's are independent, this will follow, right? And hence you can write this as 1 by n. So people usually like write this as p theta of D, so data set. And this is basically your this is what is basically your, so this is the form of MLE that you will see in books. So this is what your the whole MLE thing or maximum likelihood estimation thing looks like. Okay. And so what you are going to basically do is that you are going to basically use some SGD, stochastic gradient descent, or gradient descent, whichever is preferred. You will do this thing iteratively. So you will do theta t plus 1 is equal to theta t plus so because you are going to maximize this thing, right? So that's why I'm using max plus. So that is why there is a plus sign here. If you take the negative of it, then you can use negative minus sign here. So theta t plus 1 is equal to theta t plus eta, which is a learning rate gradient with respect to theta, 1 by n, right? Summation I equal to n log of p theta of xi comma zi. Okay. So so this is basically your MLE thing. Okay. This is the whole MLE procedure, maximum likelihood procedure. Is everything till here clear, or is there any uh,
Yes, it's clear.
caveat? Okay. Now I will so I think it's almost 2 hours. So I will just end this lecture on last one point. Okay. So note here that MLE here, so MLE, right? MLE, this thing assumes that it assume that we can see ZIs. We assume that ZIs are present in our data set, right? Here we assume that ZIs are present in our data set, didn't we? Right? So, I mean,
Yes.
if we don't have ZIs, MLE won't work, right? So now think about this, right? In general, for generative modeling, especially, right? We usually, so remember this graph that PGM that we came up that we use, right? It goes from Z to X. In a lot of cases, it is going to be the case that we won't have access to ZIs in our data set. For example, this is some example that I used last time as well. So think about an image, right? You have an image, right? You have an image. Now there are many hidden variables or this Zs, right? Z is also referred to as hidden variable, which is because you're not able to see them. There are many hidden variables or hidden factors that you're not able to see, but they contribute in coming up with this image. For example, there is an object in that image, right? So there is an object here. There is a concept of object, right? There is a concept of position of the object, right? There is a concept of camera angle here, right? camera. So there are so many factors, hidden factors that you are not able to see, but they contribute to your image, right? So you can think about this as follows, right? For an image, this is your hidden variable Z, and this is your observable variable X. Now, does this look like this thing that Z2X? This is similar to this thing, right? Z2X. This is a PGM, right? This looks like a PGM, doesn't it?
So I was under the impression that
Mhm.
Z are the actual. So if we consider the tabular data, so
Yeah.
then Z are the actual independent variables, and this X is also yet another. I
Mhm.
mean another independent variable. But then here Z is something which is not explicitly given in the data set, and probably we
Yes.
would be using some mechanism to derive a Z from the given columns, or from the given
Yes.
independent variables. Okay,
Right.
okay.
So you can, yeah, yeah, exactly. So that is exactly the point that ZIs, if ZIs are not visible, okay. For example, here in the case of image, ZIs are not visible to us. I mean, we don't have the like position or the camera angle and all these things in our data set. But we know that there are these factors that are contributing to our image, right? So our this is unlike our usual concept of MLE, where we assume that everything is present in our data set. In case of image, we have something like Z, which is not present in our data set, but we know that they do contribute in your X finally. Okay. So you can think of Zs, these are basically unknown, right? Unknown, or they are not visible, slash, not available, available in dataset. Okay. And this is your observed variable, which is present in dataset, observed variable. Okay. So in such cases, right? In such cases, Z, this is often called as latent variable, latent or hidden variable, right? So basically, you have Z, you have another node X, right? This is basically the problem of incomplete data. Incomplete data. And the question now again arises that in such cases where you don't have access to the hidden variable or latent variable, how do you how do you learn slash sample from P of X? That is the question now. For these things, we are going to see methods like elbow. First, we will see elbow. We will see then EM, and then we will see our famous VAs, variational autoencoder. So this is the plan. So I hope the stage is set right now, right? So what is the so I mean, what is the uh, scenario right now for us? The scenario is that okay, we saw something called MLE, and it works great when you have access to when you have access to all the nodes or variables in your data set. But if that is not the case, uh, for example, in case of images, right, where you have something which is hidden, which you are not able to see, then in those cases, the question arises that how do you basically learn the distribution, or how do you sample from this distribution of X? And that is the core problem of generative modeling at the end, right? So this is where we are going to stop today, right? And I think the stage is set for these new topics that we are going to see next time. Okay. So yes. So yeah. Any questions?
So would it be possible for you to share these notes today itself?
Yes, yes,
Uh,
I will do it today. It's okay.
okay.
So
And
what I will do is I will create folders in the file section of the Teams, and I'll basically put my stuff, all the stuff there.
Okay, great. And
Yes.
can you suggest some thin notes, say of 100 pages long or 120 pages long, instead of a thick complete book which I can refer for this course and can take the printout of those notes and I mean study something on my own.
Uh, I think there are some of them. Think I think there is there is one. I don't think there is one particular thing. Uh, Let me see. There's Stanley tutorial on difficulty. I think there's this one thing that yeah, I think, wait, let me just share it perhaps. This is one thing that I think should be helpful to you. I mean, it is a little, so I mean, I have read all of the things and then I have tried to sort of simplify it, but you can also read this thing. I will sort of share a lot of things. I mean, I will share a lot of resources, but I think to start with, I think you can start with this thing. So this is a tutorial basically by uh, professors, uh, s- uh, Professor Stanley Chan, and this is a great source if you want to. But I mean, yeah, I mean, you can take a look at it first. I mean, before printing out, maybe just take a cursory reading and see if you are able to understand. I think maybe after one or two more lectures, you can understand everything that is there in the tutorial. Yeah.
And the problem I face is regarding the notations. So would you be using the same notations which are given in this tutorial or the different
No,
notation?
no, I will be using my own
Okay.
notations. Yeah.
Okay.
Yeah.
Okay. Thank you so very much. Yeah.
Yeah.
Thanks. Yeah. Bye
Okay.
bye.
Thank you. Thank you. So, yeah, bye. Let's end the
Thank
recording.
you.
Sorry.
Thank you. Can you clarify IID?